Welcome to the lecture 9 for the NPTEL course on computer systems for machine learning. I will give you a brief recap on whatever we discussed in the last lecture, and then today we will discuss about more CNNs. In the last lecture, we discussed about MNIST dataset, which is one of the most commonly used dataset for these DNNs. This MNIST dataset is mainly used for digit classification, handwritten digit classification. You can see that there are multiple handwritten digits, and then the role of the underlying CNN is to classify the digits. They have to recognize the digits basically. So each of the picture has 28, or each of the image is 28 by 28. That means it has total like 28 by 28 pixels, and all of them are black and white images. So there are 10 classes, 60,000 training images, and 10,000 testing images are there. Then we discussed that LNet is one of the very first convolutional neural network which performs this handwritten digit recognition. As you can see, this is one of the like portal by AT&T, where if you just draw the digit and then it will recognize what is the written digit. After that, we discussed about ImageNet. ImageNet is one of the latest dataset which is used for, like, which is one of the benchmark. Any new DNN comes into the picture, they need to test with the ImageNet. So it is for, again, it is also for image classification. Each of the image is 256 by 256 image. They are all color images. There are total 1000 classes, and in total there is 1.3 million training images and then 100,000 testing images. Now, since the ImageNet dataset was or came into the picture, there introduced, one challenge got introduced. The name of the challenge is ImageNet Large Scale Visual Recognition Challenge, ILSVRC, where the accuracy of classification tasks reported based on top 1 and top 5 error. Then we saw that VGG16 is the one which had good performance on ImageNet dataset. VGG16 started using, or VGG16 proposed something called stacked filters. So if you remember, we discussed that instead of having one big filter like 5 by 5 filter, we can use stack of smaller filters like 3 by 3, 3 by 3 filters to cover the same receptive field. Now in that case, if we have stacked filter, then instead of like 5 by 5, if we are using 5 by 5 filter, then we have 25 weights, but instead we will just have 18 weights if we are using 3 by 3 filter. If we are using 3 by 3 filter, then the same patch is getting convolved into one particular pixel through this one 3 by 3 filter and then another 3 by 3 filter. If we had 5 by 5 filter, then again the result would have been the same. Of course, during training, the weights of these 3 by 3 filters as well as the 5 by 5 filter will be different. Will be trained differently. But the bottom line is, yes, VGG16 had many layers, these 13 layers, 138 million weights, then 15.5 billion max and all those things. The bottom line is they use stack filter. Since they have more layers, that means now we have deeper CNNs. Okay. Now deeper CNNs of course contributed to more accuracy on ImageNet dataset. But again, we will see the accuracy numbers soon, but then whatever accuracy VGG16 was having, that was not enough, and that's why we have to go deeper. If you have watched the movie, you should have you can guess what CNN we are now going to talk about. We are now going to talk about Inception. So Inception or the GoogleNet has 57 convolutional layers 57 layers in total, and out of them there are 21 depth convolutional layer. We will soon see what is depth convolutional layer. There is one fully connected layer, and then there are 7 million weights, 1.43 billion max, and then there are V2, V3, V4 version. They are all ILSVRC14 winners. So in GoogleNet, there are something called auxiliary classifier. Again, whenever we are talking about Inception, we are not talking about the movie Inception, but we are talking about the network. So Inception has 1 by 1 convolution to reduce the channel depth, and they have something called auxiliary loss. So this this is the loss in the inception module, sorry for the typo, it will be loss in the inception module. That loss in the inception module is computed by the total loss, which is nothing but alpha times real loss plus 1 minus alpha times auxiliary loss, which solves the vanishing gradient problem. So, let me go back to the previous slide. So, as you can see, this is the structure of the inception layer, inception network. Now, this network does not look like a linear network like VGG or AlexNet, right. So, it has all these auxiliary component. Now, remember, whenever we have to train these deep neural network, then the error needs to be propagated backward, right. Now, many times it happens if we have like deeper and denser network, or specifically if we have deeper network, then when the error is getting propagated, when it reaches the very few initial layers, the error becomes almost the 0, or the weight update is almost negligible, like that is called vanishing gradient problem. Now, to combat that issue, in Inception there is something called auxiliary loss. This auxiliary loss adds up to the like existing loss. So, for an example, the typical neural network, the error is only getting computed at the very last layer, but in Inception network the error is also getting computed, or there is some golden value for the middle layers, and then some error is added to the, or some what should I say, some gradients are added in the middle layers. So, that is called auxiliary classifier, which helps like with training, but they are not used during inference, they are only used during training. Now, as I was saying, the total loss is computed as alpha times real loss plus 1 minus alpha times auxiliary loss, which solves the vanishing gradient problem. The another important concept introduced by the Inception network is the 1 by 1 convolution, which reduces the channel depth. So, let us see what is 1 by 1 convolution. So, we all now understand what convolution is. We basically we will have 3D filters that will be convolved with a 3D image. I mean not 3D, yeah, I mean there can be multiple channels, yes, but ultimately it is like 3D filter, and then there can be multiple of those filters, right. Now, let us say our image size is 56 by 56 by 64, okay, the height and width of the image is 56 by 56, and then let us say there are 64 channel in the images, right. Now, in 1 by 1 convolution, the kernel size is just 1 by 1, okay. So, that is what you can see, that the kernel size is just 1 by 1, and then since we have 64 channels in the image, we have 64 channels in the filter also, right. Now, what will happen if we convolve this 56 by 56 by 64 image with 1 by 1 by 64, then all the channels will be collapsed into one channel, right, because see, when we have 2D convolution, we do element wise multiplication and then add them up. So, here we just have 1 by 1 convolution, that means it is one pixel will be multiplied with another, with the weight value of the filter in the corresponding channel, and then one number will be produced. For 64 channels, 64 total 64 numbers will be produced, and then they will get added up, right. So, the output will be 1 by 56 by 56, right, and then let us say we have 32 filters. So, that means at the output we will have 32 channels, right. So, that is how this 1 by 1 convolution works. So, basically there is no spatial correlation. So, ideally if we have convolution kernel of let us say 3 by 3 or 5 by 5, then it is trying to get the 3 by 3 or 5 by 5 patch of the image, and then performing the element wise multiplication followed by the accumulation, right. Now, if we have 1 by 1 filter, then there is no spatial correlation, right, it is just multiplying with the pixel and the weight and then adding them across the channel, right. So, that is why this can be used to reduce the number of channels in the next layer, okay. So, if we reduce the number of channels in the next layer, then the number of computations will be less. Now, the main concept of Inception V1 is to apply 1 by 1 filter before large or apply 1 by 1 convolution before large convolution filters. So, as you can see that there are multiple one by one convolutions. So, these are called one by one bottleneck. This one by one bottleneck is used to reduce the number of weights and multiplications, right. Now, just by using these one by one bottlenecks in Inception V1, the number of multiplications are reduced from 854 million to 358 million. It is like more than 50% multiplications have been eliminated just by using this one by one convolution. And again, I mean, see, the main idea is the depth of the network is still the same, or maybe it is more. So, if the depth of the network is same or more, then we probably will have same quality of training, but then the number of multiplication is reduced by a big margin, which is a great benefit, right. Because I mean, again, if the number of multiplication is reduced, then the training time will be less, as well as the inference time will be less, but with the output will have the same quality, or the inference accuracy will be similar, right. Now, as another starking difference between Inception and other previously proposed network like VGG or AlexNet is they have parallel filters. So, as you can see that between the previous layer and the next layer, probably the next layer is somewhere here, there are parallel filters. Now, these parallel filters of different size have the effect of processing images at different scales. Okay. So, maybe at using the same features which are coming from the previous layer, maybe different filters are analyzing different tone of the image, right. So, that is why it is said that parallel filters of different size have the effect of processing image at different scale. And as you can see that different parallel filters have different different parallel filter have different parameters. So, some parallel filter has 3 by 3 convolution, some has 5 by 5 convolution, some has 3 by 3 max pooling, etc. So, they are also getting processed at different scale. Some parallel filter is processing at like 3 by 3 convolution scale, some parallel filter is processing at 5 by 5 convolution scale, and so on and so forth, right. So, basically Inception network is trying to get more accuracy by introducing parallel filter and then auxiliary loss. Moreover, since they used this one by one bottleneck or one by one convolution, the number of multiplication is now less, which is resulting into less latency both during training as well as inference. Okay. But the story does not end here. So, after Inception in 2016, ResNet came into the picture. So, ResNet was proposed. Now, if you see this bar graph, you will see that x axis is showing different years ILSVRC challenge, and the y axis is showing the accuracy. Okay. Or not accuracy, the y axis is showing is the y axis is basically the error. Okay. Now, in ILSVRC 10 challenge, again this ILSVRC 10 is nothing but that challenge which was introduced with that ImageNet data set. Okay. Now, in that ILSVRC challenge, ILSVRC 10, the 10 means 2010, the error was 28.2, then the error was reduced to 25.8, but these are with shallow network. Shallow means like AliNet had 5 layers. So, some of those kind of network was the winner of ILSVRC 10 and 11. However, you can see that the error is very high, like 28.2, right. Now, we discussed AlexNet, which was the winner of ILSVRC 12 challenge. It had the error of 16.4 and it had 8 layers. Then VGG was introduced, which was the winner of 2014, which had 19 layers and the error was 7.3. Inception or GoogleNet was the winner of 2014 again, and then the error was 6.7, where it had 22 layers, right. Now, in ILSVRC 15, ResNet was the winner. ResNet stands for residual network, and it had 152 layers. It went very deep, as you can see, right. Moreover, this ILSVRC 15 winner ResNet, it had better than human level accuracy. That means it had 3.57% error as the top 5 error, but human level error is more than that. Okay. Now let us see what is the philosophy between residual network and then how the computation happens. So first of all, as you can see in the name, there is something special in ResNet, which is nothing but residual connection. Okay. So if we have, as I think when we were discussing the Inception, we already discussed that if we have deeper network, then there is a high chance that the training quality will be bad, since there is something called vanishing gradient problem. With vanishing gradient problem, the gradient update is very less in the initial few layers. So initial few layers are getting very less updates or getting updates less frequently, and as a result the overall training quality is less, right. So that is why ResNet introduced this residual network, which addresses this vanishing gradient problem. And this training and validation error actually increases more and more with more layers. So they introduce something called shortcut modules. We will see what are those shortcut modules to address the problem, right. Now there are these two figures are comparing the error during training for without shortcut and with shortcut cases. So without shortcut is nothing but you can think they are just the linear layer. They are showing two variation, one is 18 layer variation and another is 34 layer variation, and then I think the one is training error, another is validation error. So as you can see, the x axis is showing the iteration. Okay. As you can see that after let us say 30, after let us say 50 iteration, the models are converged with more than 30% error without shortcut, right. Now when we have shortcut, then you can see that after 50k iteration the error is below 30%, right. If you follow this red thin line, you see that that is the validation error with ResNet 34, that had without shortcut module the error was more than 30%, but with shortcut module the error is way less than 30%, maybe around 25%, right. So introducing shortcut error actually reduces the vanishing gradient problem, and apart from that the training quality is good, the error is lesser, right. So that is the main advantage of residual network or the shortcut modules. Now let us see what exactly these shortcut modules are. So we already have seen this 3 by 3 or some n by n convolution followed by ReLU, and then there is another convolution, let us say. Now in ResNet they have a so these are the skip connection or the shortcut connection. Now this input is actually added with the output, and then we are performing the ReLU. Okay. So that is the residual block. So that is one residual block. So the philosophy here is we need to learn the residuals. So if we just do a plain back propagation, then we will not learn anything apart from x, right. But then we need to learn something more, like we need to compensate for the vanishing gradient. Okay. That compensation is produced by this shortcut module. So in this case we are actually learning this residual, which is denoted by fx equals to hx minus x. And then when we have this ResNet 34, then you can see that these shortcut modules are actually getting repeated, right. So there are total 16 shortcut layers, and then at each shortcut layer there are 2 convolution layers. So 16 multiplied by 2 is 32, and then initially there is one convolution layer, and then at the end there is one fully connected layer. So in total there are 34 layers in ResNet 34. That is how it is named. Okay. Now these shortcut layers or shortcut modules help addresses the vanishing gradient challenge for training very deep neural network. So that is why these ResNet are very important to create a deeper and denser neural network, which will provide better accuracy with ImageNet dataset. Now ResNet also uses 1 by 1 filter. So again, if when we discussed the Inception, we saw that 1 by 1 filter is actually used before a large convolutional layer, right. So in ResNet also 1 by 1 filter is used to reduce the computation and size. So that makes the network deeper. So let us say this is the structure of the residual block for ResNet 34. Now, if we add one by one before this convolution and then after that convolution, now you can see that instead of 2 layers in residual block, now we have 3 layers. So, remember there were total, I will go to the previous slide, there are total 16 shortcut layers. So, now if we have this one by one filter to reduce the computation size, then we will have total 16 layers multiplied by 3 convolutional layer at each residual block plus 1 plus 1 plus 1, that makes it 50, right. So, that is why if we have one by one filter for residual network, that will make ResNet 34 to ResNet 50. I mean the basic principle is same, that is residual connection, and that residual thing or residual value will get added to the output before going to the next nonlinear layer. Only difference between two ResNet is in ResNet 50 there is one by one filter. Now, with respect to computation, you can see of course these, if we have these one by one filter, then I mean of course they need to I mean there will be less multiplication or less computation, but then we are introducing the shortcut module in ResNet, right. These are the shortcut module or short skip connections, right. Now, that means I will go back to the previous slide. So, let us say we have computed this x, right. Now, if we do not have any shortcut module, then probably after we compute the x, once it is used by this 3 by 3 convolution, we can forget about the x, right. We do not need to store the x until we are performing the training. But with ResNet, we cannot forget the x, we need to store the x, right, because that x, this value will actually get used later. Now, once we store it, remember none of the storage as well as the computation is free. Once we store it, we need to store in either cache or DRAM, most likely in DRAM, because the intermediate activation can be of large size. That means we need to first store, we need to first write. So, some write latency as well as write energy will be consumed. Now, whenever we are performing this addition, we need to fetch it back from DRAM. So, again some read energy as well as read latency will be performed, right. So, that is the system's implication of this shortcut module. Of course, these shortcut modules are improving the accuracy of ResNet on ImageNet dataset. Using this one by one filter, we can reduce the computation and size, but since we have these shortcut modules in ResNet, we are actually there is some implications on the hardware, there is some implication on the system itself. Now, finally, let me quickly discuss the overall parameters of ResNet 50. There are total 49 convolutional layers. So, remember the last layer is fully connected layer. There are total 25.5 million weights. Now, this number of weight is lesser than VGG. Okay. The total number of multiply and accumulate operation for ResNet 50 is 3.9 billion. I mean, of course, when I say lesser, it is lesser than VGG, but in like in general, it is very, very high, right. I mean 25.5 million means, and then each of the weight is like let us say 32 bit floating point integer, that means 4 byte, that means it will easily go to like 1 GB, right, maybe like 25 MB, and then yeah, I mean not, if not GB, then at least hundreds of MB, correct. So, I mean that is not too less, correct. And then there are 3.9 billion multiply and accumulate operation. You can imagine, I mean 3.9 billion multiplication and addition is going on. So, it is still huge, the computation is still large. And as I was saying that there are other versions of this ResNet like 34, we already discussed ResNet 34, which is some variant of ResNet 50 itself. Then there is ResNet 152, ResNet 1202 version also. Again, all these version has just different number of shortcut layers, okay, but the structure of the shortcut layer is exactly the same in each of the version. Again, these shortcut layers are introduced to have better quality of training, to reduce the vanishing gradient problem, etc., etc. So, that is all for this lecture. In the next lecture, we will talk about DenseNet, and we will see some more computational challenge and then how to address those challenge in case of DNN execution. Thank you very much.